In this video, we're going to introduce sequences and look at listing out the terms of an explicitly defined sequence. So a sequence, and here's our notation for it, which we'll get into more in a little bit. It's nothing more than really a list of numbers written as a function whose domain is just all non-negative integers. So in other words, we can write a function that will generate this list of numbers, and the only input values we will give this function are non-negative integers like 0, 1, 2, 3, etc. So no decimals or no fractions either when we evaluate our function at different values. So we'll mostly stick with positive integers, but we will see from time to time, starting with a value of 0. One of the benefits of starting with a positive integer is the first term is what you get when you plug in x equals 1. The second is what you get when you plug in x equals 2. If you start at 0, then the first term is what you get when you plug in a 0. Then the second term is what you get when you plug in a 1. So it's that offset by 1. So the function values or terms are really just written as this list separated with commas for each of the elements in it. So a sub 1, a sub 2, a sub 3, yada, 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 all the way up to the last term of our sequence if our sequence has a last term. Or if we start with 0, it's the same sequence just with a sub 0 as the starting value. So as a function, the value a of n is often written as a sub n in sequences, but we can use the techniques for evaluating a function to help us with this part of the section. And a sub n is called the nth term of the sequence, which is really nice when you start with n equals 1 as opposed to n equals 0, because then it truly is the nth term of the sequence. So we have a couple ways we can denote sequences. We can start with a sub n, or we can put it in curly braces from a starting value of 1, and then here we have an infinite sequence that we don't stop, but if we did stop, we would put it in this superscript. So we're going to list out our terms of our sequence by substituting the values of n into the sequence's definition, just like when you evaluate a function. Note, though, that we can use, just like with functions, we don't have to use f and g all the time. We can use any letter we want. So we could have like a sub n, b sub n, c sub n, etc. We can also use any letter we want instead of n. So just like we can do f of r or f of t with functions, we can also use, like, let's say, a sub I or b sub k. So we typically, for the letter that we evaluate at, we typically, around the middle of the alphabet, the I's, J's, K's, M's, and N's. All right, so example 1, we're going to write out the first 4 terms of each sequence whose explicit rule is given. So an explicit rule is nice because it just allows you to evaluate the number that you want. So the first number you plug in a 1, the second number you plug in a 2. So explicit rules are just like most functions are written. So we have a sub n equals 5 to the n minus 1 over 3 to the n. So our first term, a of 1, we're just going to plug a 1 in for n. So it'd be like if f of x equals 5 to the x minus 1 over 3 to the x, what's f of 1 equal? You just plug a 1 in for x. Here we're plugging a 1 in for n, and we get 1/3. Our second term, when n equals 2, plug in a 2 for n, we get 5/9. Our third term, when n equals 3, plug a 3 in for n, we get 25 over 27. And our fourth term, plugging in a 4 for n, we get 125 over 81. So our terms are, first 4 terms are 1/3, 5/9, 25 27ths, and 125 81sts. That's an interesting one. All right, part B, we have b sub k equals negative 1 to the k power over 2k plus 1. And here it tells us that we're going to start with k is 0 and go up from there. So this one starts with a first value of k when k equals 0. So plugging in a 0 for k, we end up with 1. Then plugging in a 1 for k, we end up with negative 1/3. Plugging a 2 in for k, we end up with 1/5. And plugging a 3 in for k, we end up with negative 1/7. So notice that first up, we alternate from positives to negatives, and that's because of this negative 1 to the k power in the numerator. Typically, when you see a negative 1 being raised to a variable power, that indicates that you're going to change your signs with positives and negatives with each new term. The denominator, 2k plus 1, generates odd numbers starting with k equals 0. So we have 1 over 1, 3, 5, and 7 in the denominators are a sequence of odd integers, based on 2k plus 1 when k equals 0. All right, part C, we have 2n minus 1, where we're going to start with n equals 1, and even though we could go forever, we're only going to list out the first 4 terms. So when n equals 1, here I just labeled it C of n since this is example 1c. 2 times 1 minus 1 is 1. When n equals 2, 2 times 2 minus 1 is 3. When n equals 3, 2 times 3 minus 1 is 5. And when n equals 4, 2 times 4 minus 1 is 7. So we get 1, 3, 5, and 7. Notice this gives us another sequence of odd integers, and that's because 2n minus 1, if we start with n equals 1 this time, that's going to generate odd integers, just like 2k plus 1 when we started with k equals 0, generated 1, 3, 5, and 7 in the denominator for the last problem. So oftentimes with sequences, you can have many different rules to generate the same sequence. In fact, there are an infinite number of ways to successfully generate odd integers, depending on your sequence rule and where you're starting. All right, part D, we have 1 plus negative 1 to the I power over I. This time we're going to start with I equals 2. Now, again, this I does not mean the imaginary I, the square root of negative 1. It's just the variable that we're using for our index. So we're going to start this time with I equals 2, plugging in a 2. Well, I should have probably made this D of 2, but that's okay. We end up with 1. And then when we go to 3, we get 0. Plug a 3 in, we get 0. Plug a 4 in, we get 1/2. And plug a 5 in, we get 0. So our first 4 terms are 1, 0, 1/2, 0. So again, just here's where you start. And in this case, we only have to go up to 2, 3, 4, and 5. So visually, graphs of sequences are very similar to graphs of functions. So here we have the sequence a sub n equals 1 over n. And because we can only put in non-negative integer values, we're not going to have any points in between the integers like 1.5 or 2.2. So for this particular function, the graph of the sequence here actually does resemble the graph of the rational function. It's just that we're not going to connect the points because for sequences, we don't evaluate like the 1.5 term or the 4.72 term. So we're only going to plug in integer values for positive integer values for n in this case. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.